let's now see some of the homomorphisms in action. So we're going to do a few examples of computing homomorphisms and some properties of these homomorphisms. So I wrote down proposition 4 because that was going to be our main tool in trying to find the homomorphisms. So remember what proposition 4 says. Give yourself a group G which is cyclic, so little x will be its generator, H any group, and then pick any element in H. Then there exists a homomorphism phi from G to H which maps x to H always if G is infinite, and if and only if the order of little h divides the order of the group G when G is a finite group. So let's try to apply it. Let's start with the following problem. Find all homomorphisms from Z to the rationals. This is a group under addition, this is a group under addition, and this group is cyclic, generated by 1, and the order of Z is infinite. So that means I'm in this first situation. So such a homomorphism always exists by saying, when I say such a homomorphism, I mean a homomorphism that takes a generator of Z, so 1, to whatever element you pick in Q. So how many homomorphisms are there from Z to Q? Infinitely many. There's 1 for each element of Q you pick. So if H is any element of Q, any rational number, then there exists a homomorphism phi sub H. I want to somehow denote this homomorphism from Z to Q such that phi sub H of 1 is H. So for example, if H is 4/3, then I get the homomorphism phi 4/3 from Z to Q. And what does it do to various integers? Well, it takes 1 to 4/3 by definition. Where would it take 2? Well, remember, 2 is the same as 2 times 1. Now, this is what I usually denoted as x to the n, right? Where x corresponds to 1 and n corresponds to 2. But because the operation in Q is addition, it's awkward to write 2 as 1 squared. Instead, we write it as 2 times 1. But remember that secretly, x, which is 1, squared. So x, when you compose it with itself using the binary operation in the group Z. Okay, so that is then, remember, phi of x, any phi of x plus n for any homomorphism, the n comes out. So that's 2 times phi 4/3 of 1. So that's 2 times 4/3, so 8/3. So phi 4/3 maps 2 to 8/3. And you can just compute any image. I mean, image of any element, let's say 200, that's going to be mapped to 200 times 4/3. So 800/3. Phi 4/3 of -5, that's -5 times 4/3, -20/3. This is, of course, just a reflection of the fact that a homomorphism from a cyclic group is completely determined by what it does to a generator. This homomorphism phi 4/3 sends the generator to 4/3. So, given this information, I can compute every other value of this homomorphism. And for every rational, we have a different homomorphism. Another example would be phi 0 from Z to Q. Well, that sends everything to 0 because phi 0 of 1 is 0. So phi 0 of any n is going to be n times 0, so 0. So this is the 0 homomorphism. Okay, so you have one homomorphism for every rational. Let's move on to another example. So, similar. That was actually example 1, not 2, but now will be 2. Find all homomorphisms from Z to, let's say, Z mod 14Z. All right, the situation is exactly the same as it was before, because my cyclic group G is still the same, it's Z. So that means there exists a homomorphism from Z to Z mod 14Z such that phi of 1 is equal to H no matter what H I pick. It's always true. So how many homomorphisms are there? There's one for every element of Z mod 14Z. So there are 14 such homomorphisms. I'm going to note them phi 0, phi 1 all the way through phi 13 from Z to Z mod 14Z. And then phi I of 1 is going to be I plus 14Z. Alright, so again, what's phi 0? Phi 0 sends 1 to 0, so phi 0 sends everything to 0, which implies that phi 0 is the 0 homomorphism. How about phi 1? Well, phi 1 sends 1 to 1. So where does it send any element? Again, that's phi 1 of n times 1. So that's n phi 1 of 1. That's n times 1 plus 14z. So that's n plus 14z. So you see phi 1 sends n to n plus 14z. What about phi 2? Phi 2 of 1 is 2. Sorry, it's not here, it wasn't really 1. It was 1 plus 14z. Plus 14z. Phi 2 of 1 is 2 plus 14z. And here, this 0, again, I mean, it's 0 in the ring Z mod 14z. So I should write really 14z here. And this also 14z. Okay, phi 2 of 1 is 2 plus 14z. So phi 2 of n, any integer, is going to be phi 2 of n times 1. So that's n phi 2 of 1. So that's n. And phi 2 of 1 is 2 plus 14z. So that's going to be 2n plus 14z. Okay, and so on. You can describe every one of these homomorphisms, what it does on an arbitrary element n. How many of them you have? You have 14, because for every element in the group H, which is Z mod 14Z, you get a homomorphism like that. So homomorphisms from an infinite cyclic group are very easy to construct. If I want to know homomorphisms from Z to any group G, how many I have, it's as many as I have elements of G. Because I can send 1, which is a generator of Z, to any element of G I want, and that will give me a homomorphism. Maybe in this case, let's do a little bit more of a calculation. I could compute, for example, the kernels of some of them. So what's the kernel of phi of 0? Well, these are all the elements of Z, which phi of 0 maps to the identity here. But the identity here is 14z. And I see that phi 0 maps every integer to 14z. So every integer is in the kernel. So the kernel is everything. The image of phi 0 just consists of 14z. Right? The range of the homomorphism phi 0 is just one element, just the identity in Z mod 14z. Let's look at phi 1. What's kernel of phi 1? Okay, let's see. All right, so phi 1 sends 1 to 1 plus 14z, 2 to 2 plus 14z, 3 to 3 plus 14z, and so on. So what would be in the kernel? Well, first of all, 0, right? 0 is going to be mapped to 14z. What else will be in the kernel? The next element that's going to be mapped to 14z would be 14. Nothing between 0 and 14 is going to be mapped to 0 in Z mod 14z, but 14 is mapped to 14 plus 14z, so that's 0 there, so that's 14. The next element is going to be 28, and so on. In fact, there's also the negatives here, right? So also minus 14 and so on. So this actually is multiples of 14. So in other words, these are all the integers such that 14 divides them. That is the kernel. What's the image of phi1? What's the range? Well, you see, phi1 is surjective, right? Because phi, where do I have it? Phi1 of n is n plus 14z. So I can get every element of z mod 14z. If I want to get 5 plus 14z, I plug in 5. If I want to get 7 plus 14z, I plug in 7. So the homomorphism is surjective. So the image is z mod 14z. Of course, it's not an isomorphism. Well, it's not injective, but it couldn't possibly be an isomorphism because these groups are not isomorphic, which means there does not exist an isomorphism between them. Let's analyze phi2. So what's the kernel of phi2? Which will be the elements? So which integers are mapped to 14z under phi2? So here's my formula. Phi2 of n is equal to that. So 0, of course, right? 0. So I'm going to just write them underneath here. 0. What else? Well, 1 goes to 2 plus 14z. 2 goes to 4 plus 14z. 3 goes to 6 plus 14z, and so on. The next integer that's going to be mapped to 14z is 7. And then the next one, 14, and so on. And also minus 7, and so on. So these will be the multiples of 7. So the kernel is actually different from the kernel of phi1. And what's the image of phi2? What is the range? Which elements of z mod 14z do I get? Do I get everything? No, right? This thing will always have to be even here. So I actually get 14z, 2 plus 14z, 4 plus 14z, 6 plus 14z, 8 plus 14z, 10 plus 14z, and 12 plus 14z. These are the only elements that are in the range of phi2. Now, this is just 3 of them. There are 11 more, which if you wish, you could analyze this way. Okay, let's try to find all homomorphisms now from z mod 6z to z mod 14z. To z mod 14z. Let's see what happens there. Well, given what you've seen so far, the first intuition might be, oh, how many will there be? 14, because I can send a generator of this group to any of the 14 elements in z mod 14z. Except that's not the case anymore, because the order of this group is not infinity, so we're not in case 1, we are in case 2. So you don't get always a homomorphism no matter what you choose here for the image of a generator. You only get a homomorphism if the order of H divides the order of G. So let's first of all, let's look at what's going on here. So this is a cyclic group generated, for example, by 1 plus 6z. What's the order of this group? It is 6. So the order of G is 6. So by proposition 4, there exists a homomorphism from z, so that's called phi, from z mod 6z to z mod 14z if and only if the image of the generator right, that is my H. H is supposed to be the image of the generator. If and only if H satisfies that the order of it divides 6. So I cannot pick anything I want here for the image of 1 plus 6z. The order of that element that I pick has to divide 6. Okay, so I look at orders of elements here. So which elements in z mod 14z have orders divisible by 6. All right, let's try to list them. Certainly 14z, because the order is 0. Sorry, the order is 1. The order is equal to 1. And 1 certainly divides 6. 1 plus 14z has order 14. That doesn't divide 6. 2 plus 14z, think about it, has order 7. That doesn't divide 6. 3 plus 14z, you have to think about it, actually has again order 14. So it doesn't divide 6. 4 plus 14z, again, will have order 7. 5 plus 14z will have order 14. 6 plus 14z will have order 7. You have to check all these. Finally, 7 plus 14z. 7 plus 14z plus 7 plus 14z gives me 14z. So the order of 7 plus 14z is 2. Order is equal to 2. That's it. There's nothing else. No other elements of Z mod 14z have orders that divide 6. The orders that not divisible by 6 have orders, have orders that divide 6. That's important. It's not the other way around. That divide 6. Only these two elements. So as the conclusion, I get that so there are only 2 homomorphisms. Two homomorphisms. So I'll call them phi 0 and phi 1 from, how about phi 0 and phi 7 from Z mod 6z to Z mod 14z, where phi 0 sends the generator 1 plus 6z to 14z, and phi 1 sends a generator 1 plus 6z to 7 plus 14z. Okay? So there are only 2. There are only 2 because there are only 2 elements in Z mod 14z whose orders divide 6. I can again analyze them. This is the 0 homomorphism. Once you send the generator to 0, you send everything to 0. So, the trivial homomorphism. The 0 or the trivial homomorphism. What about this one? Okay, so let's try to compute its kernel. So which elements of Z mod 6z are mapped to the identity in this group? So to 14z. Which elements are mapped to 14z? Remember, we're looking at this homomorphism, not at that one. So of course 6z, that's always in the kernel. 1 plus 6z is mapped to 7 plus 14z. So 2 plus 6z is going to be mapped to 14 plus 14z, which is 0. So that's 2 plus 6z. What else? 3 plus 6z is going to go again to 7. 4 plus 6z is going to go again to 14 plus 14z. So that's in the kernel as well. So this is actually the kernel, right? You can check if you plug in any of these elements to here, to phi 1, you get that, right? Because you can have a formula, so phi 1 of n plus 6z is equal to 7n plus 14z plus 14z. So you get that exactly these elements are mapped to 0, to 14z here. What about the image? Which elements are in the range of this homomorphism? Well, you either hit 14z or 7 plus 14z. You never hit anything else. So it's 14z and 7 plus 14z. So these are the only elements of the image. Let's stop here and we'll do more examples in part 2.